A tessellation is a pattern of one or more figures that covers a plane so that there are no empty spaces. So right here we see all these triangles coming together at a point, and there are no empty spaces around that point. The sum of the angles around that point, or the vertex of a tessellation, so here's the vertex of the tessellation, and here's all of the points that come together, and they're going to have a sum of 360 degrees. A regular tessellation is formed by only one type of regular polygon. So if these are all equilateral triangles, remember a regular polygon has all sides and angles congruent. So if the tessellation is made up of all regular polygons, then it's called a regular tessellation. A regular polygon will tessellate if it has an interior angle measure. So if this angle measure here is a factor of 360, meaning if I take 360 degrees, divide it amongst its interior angle measure, 60, it should come out evenly, meaning no decimals, just a whole number. So if the number of its interior angle is divisible evenly amongst 360, comes out evenly, then it's a tessellation. Okay, so to determine whether or not a regular polygon will tessellate a plane, we have to find one of its interior angles. So we do what we did from last chapter. We take all of the exterior angles, divide it by the number of sides. That'll give us one of the exterior angles of 60 degrees. But remember, one of the exterior and one of the interior angles form a linear pair. So the interior angle would be supplementary to the exterior angle. Now, we found the interior angle. We want to see if it will tessellate the plane. If it tessellates the plane, it's going to be divisible amongst 360. So we take 360 and divide it by the interior, and if it comes out to a whole number, which this will, then it tessellates the plane. So a regular hexagon will tessellate a plane. Okay, so I'd like for you to pause the video and try number 2 with a regular decagon. First, we're going to figure out what one of the interior angle measures is of a regular decagon, and then we're going to see if that number is divisible evenly amongst 360. And you should have said no, it does not tessellate a plane, because one of the interior angle measures of a regular decagon is 144, and that does not divide evenly between 360. In fact, there are only 3 regular polygons that will tessellate a plane. They are your hexagon, which we just figured out, an equilateral triangle, and your square, which is also known as a regular quadrilateral, because remember, regular means it has all sides and angles that are congruent. To determine whether or not a pattern is a tessellation, remember it can't have any empty space. So we're going to look at this figure right here, and around this vertex, this is regularly tessellated. And if you can imagine, if the image keeps going, so if the image keeps going on and on and on and on, we won't have any empty spaces, because each space will be filled with a triangle, a square, or a hexagon. So this is a tessellation. It's not a regular tessellation. A regular tessellation is made up of only one regular polygon. And clearly there's more than one polygon. Okay, so pause the video and see if you get what I get for the second example. Is this a tessellation? And if so, is it regular? And it is not a tessellation. If it were a tessellation, then you would see that these would be filled with triangles, and there are no triangles given in the original figure. So this is not a tessellation because we have empty spaces. And of course, because we haven't proved it's a tessellation, we can't say it's regular. Okay, pause the video and see if you get what I get for the last example. Okay, and you should have gotten yes that it's a tessellation, but no, it's not regular. Remember, a regular polygon has all four sides congruent, and these clearly, this looks like it's congruent to this side, but this side does not look congruent to this side. And all of its interior angles have to be the same measure. Well, this is an obtuse angle, and this is acute. So clearly these are not regular polygons, but the polygons do tessellate the plane. And the last term that you'll need to know in this unit is what's called a composition of transformations. And all that means is that more than one transformation has occurred on a figure. So what we basically are doing is putting together all of our transformations and deciding what has occurred each time. So remember when we said that our original points are just called A, B, C, and D. The apostrophe indicates A prime, B prime, C prime, D prime, where a transformation has occurred. And you can add more and more apostrophes to indicate that this was the second transformation that has occurred. So one transformation, one apostrophe. Second transformation, two apostrophes. So now we just have to watch to see. It says name the composition of transformations that maps our original to our final. So the first transformation that has occurred. Well, C is 1 unit away from the y-axis. A is 1, 2, 3 units away from the y-axis, and so is A prime, 1, 2, 3. Since each point is equidistant from the y-axis, what has happened is a reflection of the y-axis. So the first composition that maps A, B, C, D to A prime, B prime, C prime, D prime is a reflection in the y-axis. Now to get to D, from D, or to get to D double prime to D, which is actually down here, it's a translation. As you can see, it's only been slid. It hasn't been turned around. It hasn't been flipped over the axis. It's been slid. So the second one is definitely a translation. So we need to figure out how it was translated. So I'm just going to look at point D prime and go to D. So I'm going to go left 1, 2. So I take my x value and subtract 2. And I'm going to go down 1, 2, 3, 4, 5. Let me double check that. 1, 2, 1, 2, 3, 4, 5. So that means I subtracted 5 from my y value. So the translation that maps A prime, B prime, C prime, D prime to A double prime, B double prime, C double prime, D double prime is subtract 2 from your x value, or subtract 5 from your y value, which can also be rewritten as a translation vector, -2, -5. Okay, so I'd like for you to pause the video and try letter B on your own and see if you get what I get. So A, B, C, D to A prime, B prime, C prime, D prime was a reflection on the x-axis because each point is the same distance from the x-axis. From A prime, B prime, C prime, D prime to A double prime, B double prime, C double prime, D double prime was a rotation of 90 degrees. So the last part of this video is just review. I'm going to do the first one with you and then pause the video and have you do the last 3 on your own. We're going to reflect in the x-axis point 4, 2. So first I'm going to graph point 4, 2. And if I reflect M in the x-axis, that means I flip it over this axis, so it has to be the same distance away from the x-axis. 1, 2 away from the x-axis, 1, 2 away from the x-axis. So M prime would be 4, -2. Okay, so pause the video and see if you get what I get for the remaining problems. If you didn't get any of these or you're having trouble figuring these out, raise your hand or ask a neighbor. Number 5. This gives us a triangle with the points 3, -7, 1, -1, and 5, -3. We want the image of each point after a rotation of 270 degrees. A rotation of 270 degrees is a rule that needs to be memorized. We take our xy value and make it y negative x. So we flip the position of our y, make it our new x value, and we make our x value the y position but negative. So we take all these coordinates, j, which is 3, negative 7, k, which is 1, negative 1, L, which is 5, negative 3, and we take the x value, put it in the y value's position but negative, so this will become negative 3. Take the y value, and it stays positive, and put it in the x position. Okay, so you try the next 2 points on your own and pause the video and see if you get what I get. And after graphing the points, when we go 270 degrees, go 90, 180, and 270 into the third quadrant. Alright, and for the last one, I'd like for you to do it on your own, number 6. Look up the rule for a 90-degree counterclockwise rotation. What's the rule for our xy values to become our new points? So for a 90-degree rotation, we take our xy coordinates, and the y goes into the x position, negative, and the x goes in the y position, and it stays the same. So pause the video and see if you get what I get for the transformation of 90 degrees for those coordinates. Okay, and the pre-image is JKL in the fourth quadrant, rotated 90 degrees, gives us J prime, K prime, L prime in the first quadrant.